Dear friends, mathematics is a subject that enhances our visualization skills, and an important part of mathematics is observing beautiful patterns around us. So today we are going to explore some such beautiful patterns known as tessellations. The materials required for this activity are cutouts of different regular polygons like triangles, squares, hexagons, pentagons, octagons, etc. What is a tessellation? When a combination of shapes repeats itself over and over again to completely fill up a space without leaving any gaps or overlaps, it is known as a tessellation. You must have observed different tilings on footpaths, symmetrical designs on window grills, temples, and many more such symmetrical patterns which go on repeating themselves to fill up a space completely. All these examples are examples of tessellations. So friends, let us explore some tessellations beginning with the simplest regular polygon, which is an equilateral triangle. If we place these equilateral triangles in such a way that they fit together nicely and completely cover up a space without leaving any gaps and without any overlapping, it is resulting in a tessellation. We can continue placing these triangles one next to the other. Thus making a beautiful pattern which looks like this. Next, let us look at one more tessellation which is made out of the next regular polygon, which is a square. The four squares put together form a tessellation, as there are no gaps and neither are there overlaps. The pattern can continue to result in a pattern looking like the one over here. Let us repeat the same thing with some hexagons. So, if we place 3 hexagons next to each other, we observe that they have completely filled up a space without any gaps and overlaps once again, and the said pattern can continue, resulting in a symmetrical design like the one shown here. So, friends, after having explored these tessellations, the next natural question that arises is, do all regular polygons tessellate? Let us try to do the same thing that we have been doing with the set of pentagons next. If we try to place these pentagons next to each other, on placing 3 pentagons, we observe that there is a gap which is left. If we pick up a 4th pentagon to try and fill this gap, we observe that there is an overlap that occurs, and therefore we can say that this set of pentagons is not tessellating. Why is that? Because when we place the pentagons together, either it results in a gap. If we try to cover the gap, it results in an overlap. So, if I try to form a symmetrical design, even though I am able to get a design, but because of the resulting gaps, it cannot be said to be a tessellation. Let us try to do the same thing with the set of octagons. Once again, observe, if we place 2 octagons next to each other, it results in a gap. If we try to cover the gap, again I am left with yet another gap, or it results in an overlap. Therefore, even a set of octagons does not tessellate. So, friends, after having explored certain different regular polygons, some of which tessellate and some others which do not, we are ready to form the next set of observations as to why this mystery. In other words, why is it that certain regular polygons tessellate whereas certain others do not tessellate? Can you guess the reason behind that? Let us look at the set of triangles which tessellate. A combination of regular figures is said to tessellate when at any given point the combination of polygons completely covers up the space without any gaps or overlaps. What do we know about the angle around a point? We know that this complete angle around a point is 360 degrees. We also know that for an equilateral triangle, each interior angle is 60 degrees. Now, when I place 6 triangles next to each other, 60 times 6 is equal to 360 degrees, and therefore, these 6 equilateral triangles are completely covering the space around this point. Let us see if this observation holds for the 4 squares that we had put next to each other. We know that each interior angle of a square is 90 degrees, and 90 times 4 is 360 degrees once again. So, therefore, the combination of 4 squares covers up the space around this point exactly, thus resulting in a tessellation. Let us repeat this observation for the set of 3 hexagons which were said to tessellate. At this given point, we know that the interior angle for a regular hexagon is 120 degrees, and 120 times 3 is equal to 360 degrees, which is why the set of 3 hexagons is again tessellating. Now, let us see what happens in the case of regular pentagons. The interior angle for a regular pentagon is known to be 108 degrees. Now, 108 is not a complete factor of 360. As a result, when I place 3 pentagons, the resulting angle is 108 times 3, which is equal to 324 degrees. As a result, this remaining angle is the resulting gap, which is preventing this pattern from being a tessellation. Let us repeat this observation for the octagons. At any given point, 2 octagons when put next to each other, we know the interior angle for an octagon is 135 degrees, and 135 times 2 is equal to 270 degrees. When subtracted from 360 degrees leaves an angle of 90 degrees, which is what is preventing this pattern from being a tessellation. So, what do we observe, friends? That whenever the sum of angles of the combination of regular polygons is equal to 360 degrees around a point, then those regular polygons will tessellate. If it is not equal to 360 degrees, the pattern is not going to be a tessellation. Do you think you can repeat this observation for any other set of regular polygons? Now, friends, let us take our observations one step further to look at a combination of different regular polygons. Let us begin by looking at the set of octagons which we found were not tessellating. We observed that it is this 90-degree angle which is preventing this pattern from tessellating. Now, if I was to fill this gap with a regular polygon which adds up the sum of angles around a point to be 360, I know that such a polygon is a square because every interior angle is 90°, and I was to place 2 more octagons as shown. What do I observe? I observe that the figure is now tessellating, because at any given point the angles add up to 135 plus 135, which is 270, plus 90, which is 360, and therefore we have a pattern now of a combination of octagons and square which is tessellating. Let us now look at a combination of squares and triangles. So, if I place 2 squares and I place 3 triangles like this, again I have a combination of polygons filling up the space around this point completely, and a pattern which can go on repeating itself to form a beautiful tessellation. The pattern, when repeated over and over again, is going to result in a tessellation which looks like the one shown here. Let us make the observation about the sum of angles at a point. At any given point, the sum of angles is 90 plus 90, which is 180, 60 plus 60 plus 60, which is also 180, and 2 180s make a 360° angle. Let us repeat for a combination made up of a regular hexagon, squares, and equilateral triangles to fill up the gaps which remain. Thus forming a tessellation because of the lack of any gaps or overlaps. The pattern can go on repeating itself, resulting in a tessellation like the one shown here. Let us make the same observation about the sum of angles at a point. At any given point, the sum of angles is 120 plus 90 plus 60 plus 90, all of which add up to 360°. So, friends, after having explored some beautiful tessellations today, we hope you are excited to try some of your own.